Hi there, I'm Amit Banerjee. I'm an electrical engineering student at SMU.
And I'm Ryan Cole Weldon Carroll, and I'm also an electrical engineering student at SMU, and this is our 5G Vehicular Network project.
So we're in a class called Optimization in Wireless Networks, and for our end of term project, we were tasked with designing a vehicular network that consisted of cars acting as mobile nodes. Sorry, a vehicular wireless network that consisted of cars acting as mobile nodes, and it would also have a collection of roadside access points that were essentially other nodes that would carry the network. We wanted to make sure that in the event of a collision between two vehicles or a solo vehicle, they would be able to transmit critical data to the respective stakeholders, such as like themselves, the other cars, and these roadside units. So Ryan Cole and I, we developed a couple of systems that pretty well integrated help solve this problem.
Yeah.
And fine. Yeah.
And so we came up with 5 different situations of when we would need to send data between 2 different places. And so our first situation is we have a 2-car crash. And so it's car alpha and car beta are in a crash. And so what we need to do is we need to transmit data regarding the crash from car alpha to car beta. And then our next situation, we had car alpha was in a crash, either solo, like ran into a lamppost, or in a crash with another car. And so this car alpha is going to need to send data to the roadside node. And our next situation was car alpha is in a crash again, and it sends data to another roadside node. And so if it's in between 2 nodes, you're going to want to send it to both so that when authorities arrive, they'll be able to find your position. And our next situation was we have to have communication between our 2 different roadside nodes. And that way, when those 2 nodes communicate, they'll be able to tell exactly where the car is in between them. And then finally, we just have the flip of our first situation, where it's car beta sending information regarding the crash to car alpha for insurance purposes or anything like that.
So Ryan Cole kept mentioning sending the data. And it's important to know what he's talking about. Is he sending recipes, or is he sending information that can really help the authorities find out who's at fault during one of these collisions, or medical professionals can find out where the crash is happening, or insurance agents are able to find out what exactly happened at the incident. So I'm going to take you over here. We kind of call this our car code, and it's basically how we organize the data so that way, it can be it can be transmitted and received, and then processed in a way to where each individual critical data point is readable. Yeah.
And able to do something with it.
Exactly.
Yeah.
So some of the things that we wanted to identify were the GPS coordinates, basically saying like this is where the accident happened, and we wanted to get the time and date of the location. So basically a timestamp. With those 2, you kind of get at this place and at this time an accident occurred, and we are basing a lot of our systems on the assumption that these cars have built-in computer systems that are able to immediately recognize when there's been a crash, and their safety or installed safety system automatically activates and records these measurements. So we have those things. Every car that gets imported to the United States has a vehicular identification number, or vehicle identification number. We call it a VIN, and it's a 17-digit number that identifies, at least in the state of Texas and several other states around the United States, it identifies a car to be that unique car, and with required annual registrations, the authorities are able to very easily connect an individual with the vehicle. So those are 3 things that we want to make sure are properly transmitted. And one of the important ways to make sure that it's properly transmitted is by having a specific address beforehand. So when we'll talk more about our roadside nodes or roadside units or RSUs, we'll use a lot of these different words. But those will have a very unique address that will be placed at the beginning of this car code. And then every car that is linked to this system has the same address. So that way cars can communicate and they automatically know it's another car. But then they can recognize when they're communicating, whether transmitting or receiving to and from an RSU.
Yeah, a car versus a node.
Yeah.
Important distinction. And so we talked about how we're going to be sending this data, and Amit mentioned how we have unique codes that get added on before our actual car code itself to identify whether it's a car or a node. And so in order to do that, we go over here to our block diagram. And so this big block that you see here is essentially our pre-coding. And what we do there is we have to break down this long car code that Amit told you about, and we have to put it in a language that a computer and a machine will be able to understand. So computer and machine doesn't operate in decimals like we do. It can't do 8 or 9. And so it does everything in binary. And so in this pre-coding band over here, we're going to be converting this car code that we had into binary so that we're able to allow it to operate with our computer system. And in addition, that identification code that Amit mentioned, whether it's a car or a node, will be added in this machine learning pre-processing phase over here. And so after we get all of our binary data together, the next block in this process is called a DAC, or a digital to analog converter. And so now that we have this digital string of data and these digital numbers, we need to be able to send that analog through the real world. And so the way we do that is we convert these bits, these zeros and ones, into a wave, a signal that we can send through space. And so we do that by making these zeros and ones into a kind of step wave. And so for a 0, it's just going to be flat. For a 1, it goes up to 1. And based on that, you have a wave, and you're able to send information like that through our network. And so that's where our transmitter comes in. And so this antenna here, this transmitter, it would amplify using, so you're going to send voltage. It's electromagnetic wave. And through these pulses, the voltage pulses that it sends are going to coordinate to the zeros and ones. And so you're going to have that wave that you created being sent through electromagnetics voltage pulses. And it will be amplified and then sent along to the next step that Amit will tell you about now.
So I'm going to interrupt Ryan Cole's system architecture little spiel while I talk about the channel. So when we talk about antennas and we talk about electromagnetism, we have to transmit this energy across some kind of medium. And for the purposes of this task, we are using the SMU campus and the surrounding area. And today is a really nice day. It's pretty sunny and stuff. And for most of our simulations, we used what's called free space, which basically means a very unobstructed and very straightforward channel. So there's not really a lot of environmental signal loss that happens. And when I bring up that word signal loss because one of the things that we needed to do when we were looking at the channel was identify what our link budget is. So with every antenna that you transmit from and that you receive from, you have to figure out what is the link budget, meaning how far can you shoot the energy and send the data before it kind of trails off and you lose the data or you either don't get it at all. And so See, the thing is, if you just shot up the voltage and amplified at, ridiculously high gains, you could probably achieve really far distances. But the thing is, the Federal Communications Commissions, or the FCC, actually regulates the amount of gain that your antenna systems and your communication networks can utilize. And they specify it for particular purposes. So, like, ham radios have a certain restriction, and vehicular wireless networks have different ones. So, for our purposes, we were operating in the 5.9 gigahertz band, and so our maximum gain allowance was 20 dBm.
Yeah.
And so, with that, and you can look in our report and you can look through our code to see our calculations. We were able to find out that if we placed the nodes, the roadside nodes, 1,009 meters apart or 335 meters apart, we would be able to cover the entire area and make it to where there's a really quick, basically the fastest data transfer rate as possible. So that's kind of the thing with how we came up with how close our nodes and stuff are going to be. If you look through our code, you'll see, and in the report, you'll see that there's a map with the transmitters and the receivers kind of outlined, as well as some code to show you the SNR, or the signal interference to signal to noise ratios, and the coverage plots. So I'll let you get back, Ryan, to the rest of the system architecture.
Yeah. So as Amit mentioned, our signal, wherever it's being transmitted from, whether it's a car or one from one of those nodes that Amit mentioned to another one, after it's transmitted, it then has to be received. And so it's basically like that process we went through before, and it just happens in reverse. So we have this wave coming in that we coded, these pulses, and so once we have to get that back into binary, and so we do that through sampling. And so when we sample, we take measurements to match the frequency of the signal, and we're able to extrapolate those zeros and ones back, and that takes us from the analog back to the digital. And so that's our analog to digital converter, the reverse of the one we did before. And once we get back to this analog to digital converter, we can then go from these binary numbers back into numbers that people can understand. And that's what gets stored here in the node or the car computer that it was sent to. And so once we have this data here, presumably it was about a crash. And once you have that, this node can then call the police. It can phone first responders and let them know that a crash occurred and where it occurred, and call 911 and save you response time and maybe even save a life. And so Amit's going to talk about how the first responders are able to know exactly where to go based on communication between the nodes.
So when we were designing the layout of the nodes, the curbside nodes, we used what's called a hexagonal cell array, or hexagonal cell antenna array, which basically is a very efficient method of finding out how to create these rings that actually can speak to one another while being completely independent when being called or addressed and things like that. So, and one of the reasons that we did that is to take advantage of a thing that we kind of named directional memory. So if you look to this side over here, I've created 3 RSUs, or the roadside units. And the idea is, like, as a car is traveling down this road, it will receive the address for this node, the address for this node, and the address for this node. And what's happening is, when the nodes are initially installed, they are organized in a way to where it's all sequential. So if this is 001, this is 002, and this is 003. So what's going to happen is as three addresses are stored in with the car, it's going to predict what the next one is going to be, and in this case, it would be 004, and then the car will only say the 003 and the 004. So the most recent RSU and the upcoming RSU, or the subsequent one. And what's really neat about that is because it can kind of say this is where they definitely were and where they might have been. As Ryan Cole mentioned, first responders are able to triangulate the position of these individuals much more specifically because they're not just looking at what was there before, they're looking at what could be. And so when they're checking for this critical data, they're looking in the right places.
Yeah, exactly. And so Amit mentioned about how there was a crash, right? There's a crash near that node. And so that node knows there was a crash there. Obviously, it was the one that called the police. But that node doesn't only just know that there's a crash there. That node is going to remember that there was a crash there. And so these nodes are going to have storage capabilities. And so in order to store the actual car code, which is the GPS, the time, and the vehicle identification number of the crash or any crash, takes, 200 bits is what we decided?
Mm-hmm. Yeah.
And so that's an infinitesimally small amount of information in terms of what we can store today. I know you can get a 2 terabyte hard drive for like $50. Mm-hmm. And so these nodes would have storage capability, and what that allows for is to be able to store the data for crashes. So a node will know, hey, there was a crash here, and then maybe a couple months down the road, there's a crash in basically the exact same spot. And if you keep seeing crash data pop up in the memory of this node, it can then contact police or the authorities, and you'll be able to see where the problem spots are in the roads. And with that, you'll be able to fix more roads, prevent more crashes, and hopefully save lives. Because at the end of the day, that's what this is all about. It's about a better driving experience and a safer driving experience.
Sounds wonderful.
Yeah.
Thank you guys so much. If you have any questions, you can email us, I guess.
Yeah.
We were super pumped to do this project.
Yeah,
so
it's been really awesome. So we're glad we get to share some of the really awesome benefits of 5G, hopefully coming soon.
Yeah. Okay.
Thank you, guys.
Bye, y'all.